This video is very useful for both the optional final exam and the project, because if you looked at the optional final exam, the very first question was about which test you might use for a particular situation. And that's exactly what you're going to be doing in your project, dealing with some situation and then figuring out which test to use in StatCrunch. So the way I'm going to break this down is I'm going to break down the what to use when in this video, and then I'm going to break down how to do those different things in StatCrunch in later videos. And I'll put these all in one playlist on YouTube. But that way you have both those things sort of separate. So statistical tests. We have different tests depending on how many variables we're looking at and what type of variables those are. So if we're looking at a single variable, we don't want to see how two different variables are related, but we're just looking at one variable alone. Well, then we have three different options for what we might want to do. If we're dealing with just a yes-no categorical, then we could do a one proportion z-test. One thing that we would need here is some hypothesized value, right? Something that we're going to test with. If we don't have a test value, we just want to know what our proportion might be, we could also do the interval version of this. But basically, we just want to know the proportion of people who identify as Latinx, or we want to know about the proportion of people who smoke. Even if your general variable, like in the ethnicity example, has multiple levels, if we're just asking a yes-no question about that variable, does this person identify as Latinx, then we're in this situation. The next situation is if we have a quantitative variable. So now if we're looking at GPA or age, if we have a quantitative variable, the only thing we can really do is start looking at its mean. And this is when we would be doing a one sample t-test. And again, this would depend on us having some value, having something that we think it should be. We think these bags of turkey meat should weigh 1 pound. We think the average student spends $300 on textbooks a year. Whatever that might be, we have to have a hypothesized value. Again, otherwise we'd be doing an interval. Now there is one statistical test that is new. It was from part 9, still for a single variable. This one is for a categorical variable. A categorical variable with 2+ levels. So this could theoretically do the same thing that our one proportion z-test does as well. And what this test is, and this is the only new one, is this chi-square. I know it looks like chi, but we say chi. It's the Greek letter, chi-square goodness of fit test. Oops, and I'm not going to write out goodness of fit because I'm lazy. But that's what this is. I guess I'll write it out. Goodness of fit. And chi-squared you'll sometimes see written with the actual Greek letter. So what this test does is it looks at a single categorical variable and says, is it distributed in the way that we would expect? Are the proportions for every category what we would have thought? So an example that I gave was, and I do this in class, but I know for the hybrid classes we didn't get to play this game. We look and see how many people were born on Monday, how many people were born on Tuesday, Wednesday, Thursday. We do all this, right? We make a nice little frequency table of how many people were born in each day of the week. And you can see we have a single categorical variable because we're just looking at day of the week people are born. And it has, in this case, 7 levels. So we can't go ahead and just use a one proportion z interval. I mean, we could say, well, we think that more people are born on the weekdays than are on the weekends. We could try to come up with something there. But, because then we'd have weekday and weekend, we'd have like a yes, no. So our yes would be weekday. And then we could say, okay, well, we think this is going to be greater than 5 out of 7. Because we think more are born on the weekdays. So there is a way to set this up, potentially, in this land. But what we would be doing in the chi-square goodness of fit test is we'd be setting up the hypothesis that the proportion for Monday is the same thing as the proportion for Tuesday, is the same thing as the proportion for Wednesday, ... They're all equal to 1 out of 7. It's the same. It's equally likely for all of them. And the alternative, at least one is different. Doesn't even matter which one, just at least one of them is not different. So this is the chi-squared goodness of fit test. You can do this either with all things being equally likely, or the alternative is you can say, I think I know that 20% of people are born on the weekend and 50% are born during the week, or 80% are born during the weekdays, and sort of do some other math there. A lot of times you'll see these tests done with like Skittles or M&Ms, like are the proportions in a bag what we would expect. Now, another thing we could get into here are the requirements for each of these tests. Like, what do you actually need for this to be able to happen? And what do your actual hypothesis looks like? So I've given you the hypotheses for this. Hypotheses for the one proportion z-test is p is equal to, and then you have your directions depending on what we're looking for. So maybe greater than some value. That's A. Same thing here, except for it's mu is equal to. We think the average is 300, so we're just looking to say it's not 300, that type of deal. And then you have all your requirements. So for these first two, the categorical quantitative, remember, independence and less than 10% of the population, simple random sample, and then we need our sample size to be large enough that we're not hurting any of our normality type rules. So remember for this, NP and maybe I'll do these in red, your requirements. NP and NQ are greater than 10. And for this, N had to be greater than or equal to 40, or we had to have something approximately normal to begin with. And then for this last one, for the chi-squared test, the requirement is that every cell has to have at least 5 observations in it. So that's the requirement. If you have something with 0, this is a mayday. This is a problem. So a lot of times this is what will get us in trouble when we analyze our own data for the projects. And you just need to know that one thing you can do is collapse. So if you have a bunch of different categories like working 0 to 10 hours and 11 to 20 hours and 21, you might just want to collapse from 1 to 20 hours altogether so you can get a larger number in each of these little categories, each of those levels of your categorical variable. So that's a single variable. What we want to do in checkpoint 4 for the project is deal with 2 variables. And that's really all that we're able to do in Math 119. There are ways to deal with more. In fact, if you did that one online assignment where we did regression in StatCrunch, I had you do analysis with 3 variables. But that's all we cover in this class is how to compare and look at a relationship between 2. So here's where we have a lot of options, and I'm just going to go with the bigger overarching ones, and I'll talk about the special cases. So all of this comes down to what our 2 variables are. If they're categorical versus categorical, if they're categorical versus quantitative, or if they're quantitative versus quantitative. And quantitative versus quantitative is what we dealt with in part 3. We have lots of ways to handle this. We have a nice graphical display of a scatter plot. We have a good numeric measure of our correlation coefficient, which tells us the strength and direction of our linear relationship. And what we learned in the last discussion board is that there's a checkbox where we can actually get a p-value associated with this correlation. So we can actually do inference and say whether or not this linear relationship is significant if there's something going on. And then we actually have one bonus thing here. We could even, if that relationship is linear, do linear regression and then interpret our slope and all that great stuff that we learned from part 3. So quantitative versus quantitative, the only new thing that we're going to add to the part 3 stuff that we learned is this idea that you can get a p-value for your correlation. Now, categorical versus categorical, in terms of displaying this is when you want to use a stacked or a split bar chart. And I'll show you this in the StatCrunch videos, but I like to do something where we make the relative frequency, we use like relative frequencies. The reason I do this within the different categories. The reason I do this is because then it's easier to see if we had the same number in each level, if that distribution is similar. But we can talk about pros and cons to that in the actual video. So we have a stacked bar chart for our display. If we wanted some kind of numeric looking measure, we could do a contingency table, because that lets us just look at the data too. And here's the great thing. The contingency table in StatCrunch, it defaults to do a chi-squared test for independence. So this is a default that comes with this, and it gives us a nice p-value to look at whether or not this relationship is meaningful. All right, and that's just a given with the contingency table. Now, technically, part 8, we did learn about a 2-sample test for proportions. That would be a very special case of looking at a 2-level categorical and another 2-level categorical. But you can do that with a chi-squared test. So I like to tell students, just think about the chi-squared test because it's a little more overarching. A special case of it is the 2-sample proportion test that we talked about in part 8. Categorical versus quantitative. This is when you'd want to display your data using a box plot. The reason here is that we could have box plots for each of our different levels of that categorical variable. If we wanted to have some sort of numeric measures of what's going on, we could do some summary stats by group. This is what we do every single test when we look at you guys versus the other classes, right? We get the mean, the min, the max for all the classes in a row. I do this every single test in StatCrunch. In the last piece, well, how do we test all these different groups? And this is what we're going to do is ANOVA. Oops, I can't spell. So one way, ANOVA. And this will give us a p-value as well. So the only pieces here that are new is this last piece, the new one-way ANOVA and the chi-square test for independence. Now, we do need to talk about requirements and what the actual hypotheses are for all of these cases, because these are the types of things I test on. Not only knowing when to use what, but knowing what were the requirements, could we actually do this test, and what the heck were we testing for, right? Because I'm going to have you potentially come in, I'll give you a p-value and say what's the actual conclusion we can draw. So you need to know what the hypotheses are. So for a chi-square test for independence, here your hypotheses are as follows. Your categorical variable 1 is independent from categorical variable 2. The two variables are independent. This can also be just said as there is no relationship, right? Independent means one does not influence the other. Knowing one does not tell us anything new about the other one. The alternative, the two variables are related. They are not independent. The cat's threatening to step on my computer. She sucks. Relationship. Nope, don't need you. So this test, you're sitting there hoping for a low p-value, so you can say, yes, indeed, there is a relationship between the two variables. That's all you can say based on the p-value. That's very important, is that there's a relationship. You cannot tell me that girls are more likely to own a pink shirt from this test. You can tell me girls are more likely to own a pink shirt by looking at the table or looking at the stacked bar chart, but you cannot tell me from the p-value itself. It does not give any direction. Anything more is, well, based on the other pieces, here's what we can say. And that's why we do the other pieces, because this by itself is kind of sad. For one-way test of ANOVA, or one-way ANOVA, this is where we're testing a bunch of different means. So we're looking to say, is the mean for the first category, first level of our categorical variable, the same as the mean for our second, all the way up to however many things that we're comparing. So is the mean for class 1 the same as class 2, is the same as class 3? And again, this particular one is a subset of another test that we learned about in part 8, right? This is the one we did in class. We did a two-level categorical versus a quantitative, right? In that case, we were doing 2 samples. So we were able to do a 2-sample t-test. It was the same idea. So that's just a different way of thinking about it. Alternative, at least one mean is different. This doesn't tell us which one is different. Again, it just tells us that one of the groups is different from the other ones. So our one level of our categorical variable has a different mean than the rest. Again, this is why we want to have our box plots or our summaries so that we can say, according to our summary statistics, looking at the box plot, the group with the highest GPA was this group, and whatnot. All right, and the last one, the linear regression. If you wanted to set up in your requirements for this, you need your sample size to be large enough within each level, just like you would for the other kind of tests. So I think that, I can't remember exactly what that requirement is. I think it's 10 within each level. So again, this might be hard to get, but I'll have to look that up. It's definitely in the part 9. I should have it here. Hold on. Oops. I have it here. I have single factor ANOVA. There's a lot of details about the single factor ANOVA in this terrible spreadsheet. Or what is this called? Slideshow. There we go. Requirements. Ugh. Look, they actually don't even have any sample size stuff. They did say that each of the response distributions is normal, which would either mean that we have true normality or our sample size is large enough. We need to have equal standard deviations. Observations are independent. And then we have, there we go, we either need to select our random samples independently or randomly assign if we're in an experiment. So there's a bunch of requirements here that you would have to meet before you could use a one-way ANOVA. Our last one is linear regression. And here, the null hypothesis is that our correlation is 0. The alternative is that the correlation is not 0. So correlation of 0 would be that there is no linear relationship, right? And here we'd say there is a linear relationship. The strength of that linear relationship, the direction of that linear relationship are going to be denoted by the correlation itself, not the p-value. So anyways, I hope that helps with kind of what I will test on the exam, which is the different types of tests and when to use what. I'll put this particular piece of paper that I've written on, I don't know, this PDF up on Blackboard so you have sort of a note that you might want to put onto your note card. And then if you're doing your whatever the project, I will post up videos for each of these different things and how you do them in StatCrunch. So I will walk through each of these situations in StatCrunch for you.